Alright guys, so before this section we did a little bit of work with nth roots, meaning square roots, cube roots, fourth roots, things like that. We're going to do a little bit more work. This video in particular, we're going to be simplifying up radicals, learning what it means for a radical to actually be in simplified form, and then kind of play around with some techniques that we will use in order to get into simplified form. So first we've got a couple properties that we need to look at. First one is the product property of radicals. Goes something like this. We've got real numbers a and b, and then an integer n, which has to be greater than 1. That'll be the index. Like I said, it looks something like this. The nth root of a times b, you can split it up into kind of separate pieces like nth root of a and then times nth root of b. Okay, so it splits up. You can separate them up into two separate pieces and then kind of take the square root, cube root, fourth root, whatever it is, take those roots individually. So if we look at an example here, technically what we can do is we can split up that square root into all of the different pieces because we've got 25, we have a to the fourth, we have b to the ninth, they're all in separate pieces like that. So what we can do technically using this property is take the square root of 25 times the square root of a to the fourth times the square root of b to the ninth, and just break those down as much as we possibly can. So once you guys get good at this, you won't actually be writing it out like this, but just always kind of know in the back of your mind that you're using this property every single time. So square root of 25 is something that comes out nice and neat, and so we know what that is. That is just going to be 5. And then the square root of a to the fourth, here's a quick little trick here. Remember, anytime that you have a square root, the index is technically 2. You'll never see it, you'll never write it, but the index is technically 2. So we are looking for things that come in groups of 2s, products, groups of 2s. 25 is 5 times 5. That is a pair of 5s, basically. So we're trying to make these come in a pair. And so a to the fourth is a pair of a squareds. Okay, so when we take the square root of that, a to the fourth is really a squared times a squared. So when we take the square root, the quickest trick that I can teach you guys is that we're just dividing 4 by the index, which is 2, and then we end up with 2. Okay, so again, if we think of 25 as 5 times 5, then this is what comes out of the square root. If we think of a to the fourth as a squared times a squared, this is what comes out of the square root. So now, that trick that I just taught you, we can just very quickly divide 4 by 2, and we get 2. Doesn't work with this one, because this one's odd. So this one we're actually going to split it up just a little bit farther. We are going to split b to the ninth into b to the 8th, which is even, it's divisible by 2, and then just b. Okay, so here's how this is going to work. When I try to take the square root of b to the 8th, I look for something that comes in a pair. And with this, I can think of this as b to the fourth times b to the fourth. So when I take the square root, I can bring out a b to the fourth. And unfortunately, this b doesn't come in a pair. It doesn't have a buddy, it's just a single b hanging out by itself. And so we keep that underneath the square root. So this is as far as I can take this particular square root. Everything that could be square rooted was. Everything that didn't come with a pair, like this single b right here, just ends up staying under the square root. So when we're trying to get in its simplest form, the radicand, basically the stuff that's left over, it can't have any factors that have a bigger power than the index. Okay, 25 was a perfect square, a to the fourth was a perfect square. We had to keep simplifying these things down until we're left with just something underneath that isn't a perfect square. Okay, so let's do the same thing with this next group. So all of these we can split up. So cube root this time, we're looking for something that comes in a group of 3. So 25, we can think of this as 5 cubed. And then m to the 30th, 30 is a multiple of 3. So that means that m to the 30th is in fact a perfect cube. Now unfortunately when we look at p to the 20th, p to the 20th is not a perfect cube. So the way that we're going to do these problems is we're going to split up those powers into something that is a multiple of the index and something that is not a multiple of the index. So p to the 20th, here's the way we're going to split it up. We will split up those 20 powers into 18 and 2. Okay, the reason we do that is because 18 is a multiple of 3, and then these are kind of my leftovers. 20 is not a multiple of 3, so I can't use the whole thing. 30 was, so we got to leave that one just the way it was. So when we take cube roots, cube root of 5 to the third is just 5. 5 times 5 times 5 gives me 125. And then when I take the cube root of m to the 30th, remember the quick trick is I am dividing 30 by 3. So I'm left with m to the 10th. And again, that's because I'm looking for something that multiplies by itself 3 times. So m to the 30th is m to the 10th times m to the 10th times m to the 10th. Okay, p to the 20th didn't work, so we split it up. Quick trick, I divide 18 by 3, and I can bring out a p to the 6th. And that's because this is p to the 6th times p to the 6th times p to the 6th. And then these are my leftovers. I can't bring them out, so I just leave them under. Make sure you're writing your index. If your index is 3 right here, you got to make sure you're writing it right here. So that would be my final answer for this one. Okay, next we're going to move on and do some quotients. So I've got a very similar property to the product property, call it the quotient property, and this one looks very similar except just a quotient. So if I'm taking a root of a quotient like that, I have a property that tells me that I can split them up into numerator and denominator, and that'll help us with the next thing that we're going to be working on. All right, so next thing we're going to be doing is rationalizing the denominator. And this is kind of a tricky concept, so we're going to go through a couple of examples slowly here. So rationalizing the denominator, basically we're trying to get rid of radicals from a denominator, okay? So this is the process of eliminating radicals from the denominator. And if something still has a square root, remember that's irrational. So this is literally the process of making the denominator into something that is rational rather than something that is irrational. That's just kind of one of those rules that we have, as we are not allowed to have radicals, square roots, cube roots, etc. in the denominator. Okay, so the way this is going to work, to actually rationalize the denominator, what you're going to do is multiply the numerator and denominator . Multiply the numerator and denominator by a quantity so that the radicand has an exact root. Okay, so that's going to seem like a very strange sentence until we actually do something with it. So when we do something with it, it looks like this. So both these examples, the first step you're going to take is that quotient property where you split it up into two separate pieces. So this is the square root. I'm going to split it to the square root of y to the 8th over the square root of x to the 7th. Okay, so what I'm trying to do is I'm trying to make sure that my denominator is not irrational. The way it is stated right now, it's under a square root, it is irrational. So I multiply numerator and denominator by some sort of square root. Because I can't multiply a square root by a non-square root, can't multiply it by a cube root, so whatever this index is, this is going to be the same one. And I am trying to make it so that my radicand is an exact root. If I look in the denominator right now, x to the 7th, not a square root. The reason x to the 7th is not a perfect square is because my index is 2, but this is 7. 7 is not a multiple of 2, so all it's missing is just one more copy of x. If I add in just one more copy of x, then this will be x to the 8th, and then I'll be able to take the square root, and everything will be wonderful. So multiply top and bottom by the same thing. That way I'm just multiplying by a fancy one. So in the numerator, I am going to have y to the 8th times x. And then in the denominator, I am going to have x to the 8th under the square root. So now let's simplify everything we can. If we did it right, we won't have a square root anymore. So the square root of y to the 8th is y to the 4th. I can't do anything with that x because it doesn't come with a buddy. It would have to come in a pair in order to take it out of a square root. And then down here, x to the 8th, the square root of that would be x to the 4th. So I did it. I got it so that there's no longer a square root in my denominator. Now this thing is exactly the same as this thing. They are equivalent, but I had to rearrange it because I was not allowed to have a square root in the denominator. So that's the final answer there. Okay, I'm going to do the same thing with this one. Cube root though this time, so be careful with that. Make sure you keep your index of 3 when you split it up into these two separate pieces like this. Okay, so what I'm trying to do is I'm trying to multiply numerator and denominator by something. So I know it's going to be the cube root of something because those indices have to match. And then I'm trying to make sure that this thing, this thing under here ends up being a perfect cube. So 9 is not a perfect cube. 9 is 3 times 3. So I actually could use that little scribble for something. 9 is 3 times 3. I need to come in a group of 3 in order to be a perfect cube. So I just need one more 3. So I'll have 3 times 3 times 3. Here's just 1x. I need 3 of them. So here's 1x. So let me multiply in 2 more. Now when I multiply all that out, you'll see in just a moment, it will in fact be a perfect cube. So make sure you multiply top and bottom by the exact same thing. So when I multiply across, everything's still under cube roots. I get a 6x squared. 2 times 3, don't forget about that to get the 6. And then cube root of 9 times 3 is 27. That is a perfect cube. X times x squared is x cubed, and that is a perfect cube. So for your last step, clean up what you can. This stuff in the numerator is just left underneath the cube root. Neither one of those are perfect cubes or even have perfect cube factors. And then here, the cube root of 27 is 3, and the cube root of x cubed is just x. So again, same explanation as up here. These two things are equivalent. I just had to fix it so that I didn't have any cube roots left in the denominator, because I'm not allowed to have that. That's just one of my rules. So speaking of my rules, I'm going to write them down really quickly and make sure you have these. This is a really good check when you're going through and doing some of your practice problems, is to verify that your final answers can match up with each one of these. So let's write these down quickly. So we can say a radical expression is in simplified form when the following conditions are met. The index is as small as possible. So you might see some examples where you're able to rearrange them in such a way that you could even reduce the index. Next rule, the radicand contains no factors that are nth powers. So if you're trying to take a cube root, for instance, you can't have any perfect cubes in there. If you're trying to take a square root, you can't have any perfect squares in there. Otherwise, it's not simplified. 3, the radicand contains no fractions. So like example 2, I definitely couldn't leave these like this because you're not allowed to have a fraction underneath the root. And then finally, what we were just working on, no radicals appear in a denominator. Okay, so like I said, make sure you kind of keep these rules by your side while you're simplifying up your homework problems.